Kia ora te whānau. I hope you're all doing okay. Let me know if the sound is coming through all good. I can see that there's a few of us who aren't here at the moment. That's okay if you're watching this at a later stage. I hope this is helpful. Feel free to skip to any of the parts that you find most useful. But now that we're back in online learning, our focus for this week is on an investigation that we're going to do next week. So you can also spend some time this week reviewing any concepts that you're not sure about or feeling a little bit uncomfortable about with regards to the physical world topic. And if you have any questions with regards to that, please by all means bring it to our Google Meet so we can have a korero about that together. If you are watching this live, you're more than welcome to fire off any questions in the chat and I'll do my best to answer. All right, let's dive into how we do our investigations. Now, this will be a little bit of a review for some of you. We've done this a couple of times, and you're probably a little bit familiar with having done it in Year 9, so hopefully this is useful to you in those ways. This is just some details so that you know about our assessment. This will be our final opportunity to do an investigation. It's a shame we can't do it in person and collect our own data, but it is what it is, and we're making the best out of it. So it'll be one of those classic little booklets like what you've normally filled out, except this one's going to be online. We will provide you with the data from an experiment, and it will be related to the physical world topic. Your job will be to delve in to the normal things that you do, write a method, figure out name, hypothesis, all of that sort of good stuff. Take that data, process it, turn it into a lovely little graph, which you can do on paper and then upload a photo, or you can do it digitally. Once you've done that, you'll need to write about what that graph means, so write yourself a lovely little conclusion, and then do a discussion based on that information. When you've done all those things, you submit that, and that will be due at the end of next week. All right, so hopefully we're feeling okay. This week's going to be kind of easing into things, trying to refresh ourselves for the parts of investigations we most need to work on. This talk today is kind of be broken up into three parts. Firstly, it's our front half of our report. So how do we write the aim? How do we write the hypothesis? What do we even mean when we talk about a fair test? The second section is going to be looking at how we develop a good method, or how we talk about what makes a good method, because you'll need to do this. And then how do we produce a graph? Now, we spent a lot of time earlier this year talking about graph making, and it's okay. It's a skill we get better at with practice. So by all means, we can work through this stuff together, and if you've got any questions about graph making, we can always answer them at the end of the week in our Google Meet. Lastly, we'll be talking about conclusions and discussions. This is where we link our graph or whatever data that we've produced to the overall science ideas behind it, and we think about what good questions we could ask next. So let's dive into our first lesson, looking at scientific methods, in particular looking at the aim, hypothesis, and variables. Right? The first thing that actually you might want to do today, or if you're looking at this at a later stage, is to look at the investigating in science cell-wise stages. These are how we decide essentially where you're at and what you need to work on for next time. If you got a grade last time and you're not sure what you did wrong or what you really needed to move up to the next level, this is the place to look. So this particular link will take you to this set of stages, and it will spell out pretty specifically what is required at each stage for all of the parts of your investigation. The hope is that this is kind of a really transparent way for you to be able to know what you need to work on next. And we'll talk a little bit about those things as we go through. But that's there for you to have a little bit of a review, and that will hopefully help you for those next stages. So here are the major steps to the scientific method. Now, you can write these in a number of different ways, but normally the way that we do science in the real world is we start off with a question. We're wondering something about our world, something that we're not really sure about. Now, usually that can be informed by research that we've done. So scientists will sometimes start their lab reports with a lovely long piece of background where they talk about how they came to the question. We don't need you to do that at this stage, right? But we can work on that. The next thing we do once we've written our good question is we write a hypothesis. We say what we think will happen. Then we design an experiment, we collect our data, we present our data, and we we need to analyze it. We need to break down that data, and often we do that in the form of we process the data by doing things like averaging or putting it into a graph, and then we discuss what the implications of that data are. We also have a conclusion. The conclusion is where we sum up what we found. Usually we relate that to our hypothesis, and we say whether we thought we proved our hypothesis to be true, or whether we found our hypothesis to be false. Lastly, we package it all up in a neat little bow. So scientists will often present these in journals. So there'll be like a whole collection of science articles for scientists to go and read. At this stage, the way that we present it is in these kind of little booklets that you've been doing in class, or our online equivalent of that. If you need some more information on the steps of the scientific method, we've got a lovely little video here from Moo Moo Math and Science, which you can have a little look at. But let's go into these little parts in more detail. So the hypothesis is what we think will happen. Now, a good hypothesis is informed by evidence. It's informed by our lived experience. It's informed by data that we find. So when you're writing your hypothesis, we want you to justify why you think that will happen. Now, you can link this to your own lived experiences. When you get to the senior school, though, we expect you to link this to things you find online, research, all of that sort of stuff. At this stage, though, it's okay for you to say, well, I think that's going to happen because, that relates to something that I did once, something like that. Yeah? Now, your result might disprove your hypothesis. Your hypothesis might be completely wrong, and that's okay. In fact, that's a good thing in science. If you come in with an idea of how you think things are going to work, and then you find out you're wrong, that's almost more interesting than proving yourself correct, isn't it? Because it tells you that the world is just a little bit stranger than you thought that it was. So, there's two parts to a good hypothesis. It needs to be definite. Right? So really specific, really precise. It also needs to be testable. There needs to be something that it is easy to prove or disprove. There's an example here which I think is really good. It would be bad to have a hypothesis that said, I predict that yellow is the best color. Right? That wouldn't be a good hypothesis because it's not easily testable. If you had something that instead said, I predict that most people who live in central Auckland like the colour yellow, you could go and test that. You could ask that, and your threshold there would be 50%. That's most people. If you get over 50%, or maybe you define it in some other way, but that would be a testable hypothesis, whereas that other one wouldn't be. So it's really important when you're writing your hypothesis that you think about it as being something that you can test. Next up, our aim. So this is our overarching goal of the experiment. And in science, we always aim to do what's called a fair test, something that is going to tell us some truth, rather than something that's going to be bogged down in some other variables we're not intending to measure. Normally in science, the way that we do this is we keep everything constant that we can, and we tweak one thing, and we measure one thing, right? Sometimes scientists like to be a little bit tricky, but really a good experiment should be changing one thing and seeing the consequence, right? So the aim is to talk about how we're going to be, or to talk about that we're going to investigate changing this thing to affect that thing. And so you need to know what to call these particular things that you're changing and measuring, and what you're going to call the things you're keeping the same. So we're going to come to those names for variables, but you might know those already. If you're not sure, have a little think, see if we remember them. We'll come to those in a second. Something more fun in the meantime. Scientists love a good pun. They love jokes. Titles are the place to put that. You can sum up your research, essentially what your aim is, in a fun and engaging way. Now, the point of that is to get more people to be thinking critically about the cool work that you're doing. So you can kind of come up with all sorts of fun things for titles. Just make sure they're appropriate and kind of tell you something about the nature of the work that you're presenting. So there's all sorts of fun ways to do this, but this is a space for a little bit of creativity. So we've got an example of kind of those three things broken down. Lovely example here. What's the hottest part of the flame? You could have some sort of funky title. and you hypothesize that if you place some water in a test tube in one part of the flame, it's going to heat it up faster than if you place it somewhere else in the flame. That's a nice testable hypothesis, isn't it? You can have your own go at this, and I would encourage you to complete this because this will be good practice for you. These are 3 examples in the slides. Complete them in the slides, and I will come through and give you some feedback at the end of the week. Hopefully that will help you to make sure that you're on track for completing this when we do this next week. Now, we spoke a little bit before about these things called variables, things that can be changed. And in science, we like to change one variable at a time. If you change more than one variable, it becomes hard to know what the cause is or what's going on at the root of the problem. We have 3 words, and hopefully we were able to think about these. The thing that we change, the variable we change, is called our independent variable. The thing we measure, the variable that we measure, is called the dependent variable because it depends on the one that we've changed, right? So we've got our independent that we tweak and our dependent that we measure. The controlled variables are the things we control, the things we keep constant. And if we do a good job, we try and keep those controlled things as controlled as possible. We don't want them to change. As soon as they change, they can have negative impacts on our experiment, which is not so good. That's what we call a fair test, when you do a good job of controlling all your variables, tweaking one thing and measuring one thing. Lastly, when you're talking about these variables, particularly your independent and your dependent, it's really important to describe them with units. If we're going to change temperature of a flame, for example, we need to measure that in some way. We might use Fahrenheit, we might use Celsius, we might use Kelvin, but we need to say we are measuring temperature in Celsius, or we're changing temperature in Celsius. That's our independent variable. And our dependent variable might be, depending on the nature of your experiment, something like the volume of gas that is made. And you measure volume in things like litres or in cubic centimetres or cubic metres. Whatever you want to do, but you need to specify that. Okay, so we've got an example here. So here we've got a lovely little experiment looking at which brand of fertilizer is the best for growing strawberries. So your independent variable, the thing you change, is the category or the type of fertilizer you put on. It's a nice little categorical variable, right? So you could have 5 different fertilizers, and they might have different amounts of certain things in them, but you could test that. So that would be your range. And for that one, the unit kind of is the fact that they're categories, which is nice because it's less work for you. The dependent variable might be something like the number of strawberries, in which case you'd measure it with a number, the number of strawberries that are grown. You could equally do this with the weight of all the strawberries that are grown, because maybe some plants make a whole bunch of little strawberries and another plant makes one big strawberry. So you could measure it in terms of weight. And you measure weight in things like kilograms or grams. You could also measure it in pounds, but it's up to you, as long as you're specifying the variable there. You also want to keep everything else constant. So this is where you start to get creative. What things do I need to keep the same? And that could be things like the amount of sunlight they're exposed to, the humidity of the air, the place that you're putting them, the amount of water you're giving them each day. Because if you start to give one plant more water than another, that might put it at an advantage, and that might compromise the fairness of your experiment. So there's some opportunities in the slides here for you to practice a whole bunch of these. And I will give you some time to work on that, and I'm happy to give you feedback. Additionally, at the end of all of those is a space for you to watch a lovely video on big experiments. This is like a little extra for experts. We'll have a number of these in the slides for you to have a look at if you would like to. So, to sum up things, we've got 2 final tasks. The first thing is looking at aims and hypotheses. So if that's a task that really appeals to you, if you need to work on your aims and hypotheses, that's a good one to look at, and that Quizlet will help you out with that. The next one, which is probably the more challenging one, so if you're a big brain, I would attempt this one, is a variable worksheet. Looking at those different variables and identifying which one's the independent, which one's the dependent, what are you going to control, that sort of thing. All right, now we're on to methods and graphing. Little starter task based on the previous lesson, so you're welcome to pause the video and have a go at that if you would like to. But we're going to move on to the answers for this one, which is in this case shown on the screen here. But we're going to talk a little bit about methods. So methods are kind of like recipes, right? There's sets of instructions which we follow in a sequential order in order to conduct an experiment. You ideally want your method to be so excellent and so clear that somebody else can follow it even if you're not there. Here is a good example of a method. Notice that it's quite succinct, but it's really specific. It's really specific. And it would be really hard to mess this one up. They also provide a lovely equipment list, which is helpful. Different scientists have different ways of writing these things, but this is a nice way to follow, particularly to get used to that idea of writing a nice, straightforward method. This is a little video. I don't think we've shown this to you, but we might have done. So this is a little peanut butter and jelly experiment. If we remember this, you can let me know. I would encourage you to watch this video. I'm not going to spoil it, but this is kind of an exercise in how to write a good method. So once you watch this video, have a go at answering these two questions, looking at why it's important to talk about good, or why it's important to write really good methods. Okay? So now we're going to look at graphing. So graphing has, we've spent a lot of time on graphing in class, so I'll try not to spend too much time on it. But essentially, it's a skill that you get better at over time. The first rule of thumb is if you're doing it on paper, you need to try and use a pencil and a ruler to make sure that you're being as precise as possible, but you can also rub out your mistakes. We have a set of things you need to include, but the key rules that sometimes students mess up is you only plot your averages, the reason being that it best represents your data. If you do advanced statistics, I'm talking year 12, year 13, they sometimes represent how much error there is in your average using these things called error bars, which are pretty funky, but we don't need to do that at this stage. And we would encourage you all to have a go at drawing a line of best fit. A line of best fit is a line that best fits the data. Wow, who would have seen that coming? So I'm going to show you an example of a graph that does everything well except the line of best fit. So here we've got a lovely little graph based on this data table in the top left. It has a title. Each point is coming from an average of 3 different points. It's got its dependent and independent variables identified. They're on the correct axes. They both start at 0. Those independent and dependent variables both have units described like in little brackets next door. It's almost perfect, except for their line of best fit. They've just connected the dots. That's not a line of best fit. So a line of best fit, in our case, we're only going to really be looking at straight lines, linear lines of best fit. There are more advanced ones, but at this stage, that's all we really need to be doing. The one on the right here is a perfect example of a line of best fit. So the student has drawn a linear line where they've tried to keep the error equal above and below. It doesn't have to be perfect, but you have to try and do your best to draw a line that best represents the overall trend of the data. Is the data going up? Is the data going down? Now we have terms to describe that. If the data is going up on average, that's a positive correlation. That means that as your independent variable goes up, your dependent variable goes up as well. If it goes down like this, that means that your independent variable is going up, and that's causing your dependent variable to fall down. So that would be an example of a negative correlation. Sometimes we investigate something, we find that they don't relate to one another, in which case we would say that there is no correlation. That usually is accounted by a whole bunch of points all over the place, and it doesn't look like there's any overall trend going up or down. So we would describe these graphs here as an example of positive correlations. With lovely lines of best fit, these would be at the sort of 5E level. So that's where you're really shooting for there. Okay, a little bit of an extra for experts for those of you wanting to look at the year 11 sort of content. This is an investigation at level 6, so this is kind of next year stuff, but you're capable of this. So take a little bit of a look at that. Here are two little tasks you can look at. You could have another go at writing a better peanut butter and jam method if method making is probably the part you need to work on most, or spend some time reviewing these graphing exemplars. This is kind of if that's the part that you need to work on most. So now we're on to our last little section. This last section here is on conclusions and discussions. So this part is the kind of writing-y part, and for some students they find this part really easy. For some students this is the most challenging. That's okay. I would encourage you to focus on the parts of this video that you find most valuable for you. As we always do, we start with a reference to our previous lesson. So here we've got an example of a graph comparing the temperature of a house to the monthly cost of power bills. This is from a particular location where it's normally quite cold, and so as the temperature that you wanted to keep the house at increases, the monthly power bill cost also increases. So this would be an example of a positive correlation. We can also see that they've done a lovely job of having a line of best fit, because this line kind of has an equal number of points above and below. It's spreading out the error, right? So in the example of the conclusions we give you, we try and scaffold them so that when you're not having to write them all from scratch. So you're talking about how as one thing increases, the other one increases as well. And you can look at sort of starting to do those kind of calculations around the line of best fit if you're feeling brave. So spend some time on this if you need to. So first up, the conclusion. The conclusion is where we use the data from the graph to essentially do what we just did before, right? To communicate the overall trend and what that means. The most important part of this, because we've just done that just now, but once you've done this, you need to talk about whether that supports or does not support the hypothesis that you proposed. So you would have written a hypothesis at the start for your experiment. It's your job to say, this data supports or this data does not support my hypothesis, and to understand why that is. So have a little go at that. This is an example of a scaffolded kind of bit of practice. I'm happy to give you some feedback on your discussion of your hypothesis. The next part of our discussion always looks at what we could have done better. So in this case, it's going to be a little bit tough because you're going to be writing a method for an experiment that's already been done. But imagine that you're in a space where you have to come up with your own experiment, right? There's going to be things you can work on. Even the greatest scientists in the world will talk about the things they wish they would have done better, because we're constrained by the fact that we only have a certain amount of money and a certain amount of time to be able to do these things. I'm sure we'd all love to have perfectly sterile rooms with perfect equipment, but that's just never going to be the reality. So we can talk about what difficulties we might have occurred, what things we wish we could have done better, what things we think we would do better next time, all of that sort of stuff. That all goes into what we call an evaluation of the method. Once you've done that, you can talk about the links between the science and what you saw. So this is where you bring in all that beautiful knowledge you've been learning about this year, and you can start to relate that to what you've seen. This is really where also we get to see your excellence level thinking, because you're going to be linking to concepts outside. So the question is, why did you see what you saw? And how do I use my science knowledge to demonstrate that? When you're getting into year 11, so those of you shooting for level 6 of the curriculum, you can start to look at outside references for this. So you can start to look at websites or articles where people talk about these things. At this stage, though, if you're just using the science knowledge you learn in class, that is absolutely fine. Okay, so have a little bit of a go. This is an example here talking about how particles bump into one another as evidence for why heating up water causes it to get hotter, essentially. The last section of your discussion is what you talk about in terms of your next steps. This is an opportunity to be creative again. You look at what questions has this got you thinking about. A really great experiment should leave you with more questions than you came in with, more things for you to think about, to ask in terms of those next steps. This is where you can say, I really wish we could have done an experiment where we investigated this thing or this other thing. or whatever it may be. So you can put that in there. There is a space here for you to have a go at that if you'd like some practice. Have a watch of this video and then write out some, just some ideas in terms of what experiments you'd like to see done in the future. There's an additional Extra for Experts video here as well, and a final little task for the week. This is an options task where you can either write another new method or you can discuss the science, whatever you need to work on most. And that brings us to the end of the content we needed to go through this week with regards to investigations. Now, I hope that this has been helpful. By all means, skip back to the parts of the video that you find you will need to work on most, and bring any questions you may have to our Google Meet on Friday. Lastly, I think it's really important to say this has been like a long and hard lockdown. I hope you all are looking after yourselves, spending time with your whānau, doing all the various things you need to do to keep your mental health in check. We'll try and make sure that science this term is as fun as it can be under the circumstances, and we're going to do our best to keep you engaged, okay? So thank you all very much for hanging out here today. I'll leave you be. I'll see you on Friday.